partial derivatives. The topics of this section is partial derivative. Actually, we know how to differentiate many kinds of the function of one independent variable. For example, trigonometric functions, exponential functions, polynomials, etc. And how to interpret the derivatives that result. You know that it's the rate of the change of the function value. So if your function represents the cost, derivative is the marginal cost, or if it is revenue, derivative of the revenue is the marginal revenue, etc. And we discussed all detail of the derivatives in the first term. What about functions with two or more independent variables? I gave an example about the surfboard. You can remember we have two type of the surfboard. One of them standard surfboard, the other of them is the computational surfboard. So for this surfboard, we have already write the cost function with the two variables x and y, 700 plus 70x plus 100y. Here x represents the demand of the standard surfboard, y represents the demands of the computational surfboard, and 700 is the fixed cost for the both surfboard. Okay, as I remember, 500 fixed cost for the standard surfboard, 200 is the fixed cost for the computational surfboard. Now, suppose that the differentiate with respect to x holding y fixed, and denote the resulting function by c sub x of xy. Okay, so here we differentiate with respect to x by holding y fixed. So 700 is fixed, so derivative of the 700 is 0, and derivative of the 70x is 70, and 100y, y is constant, so 100 is constant, so we consider y as a fixed, so this is also 0, so that is 70. And similarly, by we can differentiate with respect to y by holding x fixed. Okay, so c sub, and we denote by the c sub y, x of y. Derivative of 700 is 0. Derivative of 70x is 0 because x is constant. So the derivative of the 100y is 100. So this is 100. Each of these functions is called a partial derivative. And in this example, each represents the marginal cost. For the one variable, derivative represents the marginal cost. So if we consider the one variable case for the standard boards, okay, this is 500 plus 70x. For the other boards, 200 plus 100x. So here c prime is the 70. So here 70 is the marginal cost. So this is a marginal cost for x. This is marginal cost for y. So this one, the first one, is the change in cost due to a 1 unit increase in production of the standard board with the production of the computational model held fixed. The second one is the change in cost due to a 1 minute increase in production of the computational board with the production of the standard board held fixed. In general, now we can talk about the partial derivatives of any function with respect to x by giving the definition. Okay, so in general, if we have a function z equals f of xy, okay, so the partial derivative of f with respect to x, sometimes it is denoted the partial z, not the normal, the partial denotation is different, dz dx, okay, remark, not dz over dx, okay, dz over dx, or f sub x, or by showing the independent variable f sub x o x y. And the partial derivative is defined by the following limit, okay, so dz over dx equals limit h goes 0 f of x plus h y minus f of x y over h. So you are familiar with this notation. If you don't see the y variable, so we don't focus on the y, okay, so this is just the derivative of f with respect to x. But here f has a two variables, so we show that the y here, so we consider y as a constant, okay. So provided this limit exists, we can say this is the partial derivative, okay. So provided that the limit exists, you can recognize, as I said, this formula as the ordinary derivative of the f with respect to x holding y constant, okay. So we can continue to use all derivative rules and properties which is discussed in the first two chapter I don't remember, some chapters in the first week, okay, and apply them to partial derivatives. So similarly, the partial derivative of f with respect to y, which is denoted by dz, partial dz dy, or f sub y, or f sub y x of xy, okay, is defined by the similar limit dy, limit key, instead of the h we write key, but you can use the h, does not matter, f of, now we fix the key x comma y plus key minus f of x comma y over key, if this limit exists, okay. Again, we can say that this is the derivative of the z with respect to y. In the calculational viewpoint, everything is easy. You consider y is a constant when calculating derivative of the f with respect to x. You should consider x as a constant when calculating derivative of the f with respect to y, okay. In the problem solving hour, I will solve some question related with the partial derivatives. Now, let's consider the geometrical interpretation of these derivatives, okay. Partial derivatives have simple geometrical interpretations, actually. Let's consider the graph of the functions. Let's show that this graph, okay. So on the Cartesian coordinate system, x, y, z. So if you hold x fixed at x equals a, okay, here let's fix x equals a. So x is fixed. X is fixed. So we can y change. So the graph of the y for when x change when x constant a yes, y change. So this is the y values, okay, y change. So for example, here we have this part of the graph, okay, so y change here, this is that part, so this is our graph. So derivative of the f with respect to y at the point a comma y represent the slope of the curve obtained here, okay, so I mean here this slope of this tangent line is derivative of the f with respect to y at the point a comma y, because y change. If you fixed y equals b, for example here y equals b, so x change among to this line, so this is the graph of the, for example this curve is the for the point on that line we have this curve on the surface, okay. Actually the surface is z equals f of x y, okay. This point is y equals b. So which color should be used? Okay, let's find the good color. Okay, let's use this color. So the tangent line at that point is this one, okay. So this is the slope of this line, tangent line is f sub x x comma b, okay. You can observe easily this intersection point is the point a b and f of a b. By this point is a comma b, so the value of to this point, okay, is the f of a b. This is the z value, z is f of a b. So the interpolation of the partial derivative like this one. On the other hand, we can talk about the second order partial derivatives, of course. Second order partial derivatives. If our function equals z equals f of xy, okay, you can calculate the derivative of the derivatives. I mean, for example, first we calculate derivative of the z with respect to x, okay, or this is denoted by the f sub x xy. Then you can calculate derivative of this function with respect to again x, okay. I mean derivative of this function with respect to x, z dx. So this is second order partial derivative. We denote by this one d square z over dx, or some books say df dx. Okay, this is also correct, okay. So it can be denoted by also this one. So this is the second partial derivative with respect to x and x, okay. For example, if this function is x to power 5y squared plus 2xy, okay. So derivative of the z with respect to x is y is constant, so 5x to power, for derivative of the x to power 5 y squared plus here derivative of the x is 1, so 2y. And here we calculate derivative of this function with respect to z. So this function is 5x to power 4y squared plus 2y. So this equals y squared and 5 is constant. So a derivative of x to power 4 is 4x cubed. So 5 times 4 times x cubed y squared. 2y is constant. So this is 0. So 20x cubed times y square is the second derivative of the f with respect to x and x. Okay, it's 2 times we differentiate with respect to x. For example, you can differentiate this function with respect to y. Derivative of this function with respect to y can be calculated also. So from here, by differentiating this function with respect to y, now 5x to the power 4 is constant. So derivative of y squared is 2y. Plus derivative of 2y is 2. Okay, so 10x to the power 4y plus 2 is the derivative of the z, first with respect to x, then with respect to y. As you know, we can calculate derivative of f with respect to y also. So here, derivative of the z or f with respect to y equals, now x term should be considered as a constant. So x to the power 5 times derivative of y squared 2y plus derivative of 2xy is 2x, because we consider 2x is constant, derivative of 2y is 1. So from here, by differentiate this function with respect to x and y, you can calculate the another derivatives with respect to x, derivative of 2z with respect to y. So from here, by differentiating this function with respect to x, 5x to power 4 times 2y plus derivative of 2x is 2. 10x to power 4y plus 2. Actually, these are the same. This is normal. Always this is correct for the continuous differentiable functions. Okay. So here, as you see, derivative of 2z first with respect to x, then with respect to y equals derivative of second derivative of 2z first with respect to y with respect to x are the same. Okay. In general, we denote this situation. This is yx, sorry, first y then x. This is f first we differentiate x, then y. First we differentiate y, then x. Okay, so here, this is the first. This is the second order. This is here. This is the first. This is second order. Okay. So in general, we can say that f sub xy equals f sub yx. This is always correct. Okay. And also you can calculate derivative of the z. You can calculate derivative of this function with respect to y. So second derivative of the z with respect to y. So that equals derivative of the obtained function, derivative of the z with derivative of the this function with respect to y. So what is that one? Here, derivative of 2y is 2, so 2x to power 5. Derivative of 2x is 0. Okay, so 2x, I'm sorry, 2x to power 5. 2x to power 5 plus 0. Okay, so also this can be calculated as you see. So again, let's write our notations. So derivative of the f sub xx equals derivative of the f sub xy, which is second derivative of the z with respect to x square, or you can use this notation. There is no z, sorry, dz dx. Okay, or for f sub xy, f sub xy of xy, second derivative of the z, first we differentiate with respect to x, then we differentiate with respect to y. So this is dy dz dx. Okay, actually the reason here we write the d square, here we write the x square. As you see from here, we have the partial d. So this is the partial d square. Here we have dx, so this is dx square. Actually dx square means is that one, but never we use the brackets here. Okay, and you can write similar notations dy for dy dx and dy dy. Okay, you can write. If you want, you can look your textbook.